Welcome to the video lecture on using a graphing calculator to graph equations. For some graphs, we're going to want to be able to graph them by hand, and for some graphs that are especially messy equations, using a graphing calculator can be a very helpful tool. So in today's lecture, we're going to talk about how to do some of the basic graphing on a graphing calculator. Now, it's important to still have a good idea of what to expect a graph to look like, because graphing calculators can only show us a particular window of the graph at a time. If we're not looking at the right window, then we may miss out on some of the important information about our graph. So let's start with a fairly basic equation, y equals 2x plus 10, and we're going to graph it by hand, noting the x and the y intercepts. So to graph this equation by hand using intercepts, we can easily do that with a table. And intercepts are zeros. The y-intercept would occur when x is 0, and the x-intercept would occur when y is 0. So if our equation is y equals 2x plus 10, and I plug in a 0 for this x, this entire x term will go away, and I'll be left with just y equals 10. If I plug in 0 for y, we would get the equation 0 equals 2x plus 10, subtract 10 to the other side, divide by 2, and we get x equals negative 5. So our x-intercept is at negative 5. Now, since my graph here is not very tall, I'm going to use a scale of 2. So I'm going to go by 2's on the y-axis, 2, 4, 6, 8, 10, and my y-intercept was at 10, so I'm going to put a dot. And then for my x-intercept at negative 5, I'm going to go by 1's, so negative 1, 2, 3, 4, 5. So I'm going to put a dot at negative 5. And my line would look something like that. Okay, so now if we take this same equation and we put it on our graphing calculator, then the first thing you want to do to graph something on your calculator is use the graphing keys, which are up across the top here. And whenever you want to type in an equation, you're going to hit that y equals button. And sometimes you might have some old stuff already stored in your calculator, like I do here. So I'm just going to hit clear, and that immediately clears it out and allows you to type in whatever you want. So I want to type in 2x plus 10. So I'm going to hit 2, and to get the x, the easiest way to do that is to use this button right here, the x, t, theta, n button. That's your variable key. So you hit it once, and then we're going to add 10 to this. Now what I'm going to do is just graph this in a typical window. Let's look at our window dimensions. That's again right across the top here. And mine are all sort of varied here from the old example that I had typed in before. So a quick, easy way to get to what we call a standard window is to go to Zoom, and you'll see it's option number 6 here. Now either you can arrow down to number 6 and then hit enter, or you could have just pressed 6 right from the very start. And there is my graph. Now notice I have some dots in here. Now that's because I had some of my format issues. So I want to show you how to adjust your format in case yours looks a little different from mine. And typically on my graphing, I don't normally have these little dots showing up. So just to show you some of the graphing options, let's go to format, which is in blue up here across the top, right above zoom. So if I hit second zoom, that will give you some of the graphing options. And typically what I usually start off with is everything on the left side highlighted. So if I turn that grid off, then I'm not going to see any of those little dots anymore. So let's hit graph, and there's the graph of my line. And this is typically how I look at my graphs initially, unless I need to do something special with it. So there's my graph. Now let's take a look at the particular window where x ranges between negative 1 and 1 and y ranges between negative 1 and 1. So instead of looking at this window, which notice is negative 10 to 10 for the x's and negative 10 to 10 for the y's, I'm going to change this to just be negative 1 for the x min and positive 1 for x max. So that means your smallest x will be negative 1 and your largest x will be positive 1. This XSCL stands for x scale, and that's just telling you how far apart your little tick marks are going to be. So we're going to put our tick marks or our scale 1 for every 1 unit. And now I'm going to arrow down and go to my y min and change that to -1 as well, and change my y max to +1. Your mins should always be smaller than your maxes. And this XRes stands for X resolution. Usually I just leave that at the default value of 1. So now let's take a look at our graph. And you can see some tick marks here. I've got a little mark on the left, that's -1 for X, and the mark on the right is +1 for X. The little mark on the bottom is -1 for Y, and +1 for Y. So what this shows us is that I don't have any part of my line showing up in this window. This would be a zoomed in version of my graph. If we go back to our hand-drawn graph over here, remember that -1 to 1 for x's would be just between here and here, and -1 to 1 for y's would be from here to here. So we're looking at this little rectangle right here. And you can see that the line that we have drawn does not go through that tiny little window. So having the appropriate window dimensions will enable you to see the right part of the graph. And if we make our window too small, we may miss out on the entire graph completely. Okay, so in this example, what did we end up seeing? We saw nothing between -1 and 1 for x's and y's, because that's just too small of a window, and our graph did not intersect or go through that small window at all. So if the window is too small, we may not see the solutions to the graph. Likewise, if our window was too large, we may lose some of the detail of the graph and be misled by its simplicity. So we're going to see examples of that as well. So the window dimensions are extremely important when you're using your graphing calculator, because you don't want to get misled by your calculator. It's not always correct unless you're typing in the correct dimensions or appropriate dimensions for your particular graph that you want to look at. So let's take a look at another graph. This time we're going to enter in the equation y equals x squared plus 7x minus 60, and this time we're going to type it into our y2 on our calculator. So if you ever want to type in an equation, you want to go to your y equals button. Notice in y1, that's where we had that 2x plus 10. So this time I'm going to arrow down, and in y2 I'm going to type in x using that variable button. And I want x squared, so here's my square button. So I'm going to hit x squared plus 7, hit my x button again, and then minus 60. Now if I hit graph right now, it's going to use that same window, -1 to 1, -1 to 1, that we were using before. And it's also going to graph both of these equations at the same time, because both of these equal signs are highlighted. So let's first fix our dimensions so that we can see a standard window. And remember that the easiest way to do that is to use that zoom standard command, which is under zoom across the top here, number 6. So I'm just going to go ahead and hit 6, and that automatically makes my dimensions -10 to 10 for the x's, -10 to 10 for the y's. And this is what we see. Now remember from the last example, this sort of diagonal line right here was that 2x plus 10. So this piece over here must be part of my y equals x squared plus 7x minus 60. Now let's go back to our y equals, and so that we don't get too confused, let's turn off the graph for 2x plus 10. So to do that, you arrow over to that equals so that it's flashing, hit enter, and now if you arrow down, you should see that only the equals for y2 is highlighted. The equals for y1 is turned off. So that means it's only going to graph y2. So let's go back and see what our graph looks like. So this is our graph. Now if we look at that, is that what you would expect to see for an equation that has an x squared in it? Well, what do x squared graphs usually look like? We know that x squareds should be parabolas or U-shaped. And since this is a positive x squared, we should be expecting to see a U that points upwards. So obviously we're not seeing that U shape, so we must not have an appropriate window here to get a good graph. So we're going to need to experiment a little bit with what would be a good window to use, and that's probably the hardest thing about using a graphing calculator, is figuring out what is the best window dimensions to use. So one thing that I like to do is experiment a little, but also use appropriate choices that would make sense for the problem. And one easy thing to look at, if you look at this equation right here, are the y values and the y-intercept. Think about the y-intercept for a moment. Y-intercept happens when x is 0. So if I plug in 0 here and here, these two x terms disappear, and we would just be left with -60. So the y-intercept is at -60. And that means the graph goes through that point, 0, -60, at least. So it's got to go at least as low as -60. And if we look at our window dimensions, our y min, which is our smallest y in this window, only goes to -10. So that's part of the reason why we're not seeing this complete graph. It's because our graph isn't going low enough to even show us where that y-intercept needs to be. So let's arrow down and let's change our y values. Now we know it needs to go to at least -60, but there could potentially be lower points as well. So a lot of times what I'll do is I'll round off to the nearest 10 or hundredths that's closest to the y-intercept. So if I know I need to go to -60, I might lower that a little bit and go to -100. So get a little bit of buffer space. Now just to equalize that a little bit, let's go and change our y max to +100. Whoops, too many zeros there. Now if I leave my y scale at 1, let me just show you really quickly what that's going to do. If I hit graph, notice this big, thick black line. That's because it's trying to show little tick marks every 1 unit between -100 and 100. That's a lot of little tick marks. So probably to avoid a thick black axis like this, you want to boost up that y scale so it's not quite so small. Now before we do that, let's also take a look at our x's. We're starting to see this U shape, but it looks like we're missing part of where this graph wants to hit the x-axis over here on the left side. So potentially we probably want to expand our x min, the left dimension on that window, a little bit lower or a little bit more negative so that we can see exactly where it's going to hit that x-axis. Because knowing where those intercepts are is important information about our graph that we would want to know about. So let's go back to our window. Let's go ahead and fix our y scale before we forget. So instead of going by 1s, let's maybe boost that up to going by 10s. Or you could use 20s or 50s, anything like that. Now for my x's, remember we couldn't see that x-intercept on the left side of the graph. So we might want to make this a little bit smaller or more negative so that we can see this properly. You can experiment here a little bit if you wanted to just go with -20 and keep that x max at 10, that would be fine. And you can always come back to this window and adjust as necessary. So let's hit graph. And now we can see exactly where that x-intercept is on both sides, and it has this typical U shape that we would expect for a parabola that points up. So here are my dimensions. For x's, my window dimensions were -20 to 10. Notice here I'm using interval notation, smaller number on the left, larger number on the right, and my y's ranged from -100 to 100. Okay? So by playing around with that window, we were able to adjust it so that we could see a good, accurate, complete graph. All right, let's try another example. This time we're going to graph y equals x squared plus 10, and we're going to do it in each of these 4 different windows. So let's go back to our y equals, and let's go ahead and clear out both of our previous graphs. And in y1, I'm going to type in x squared plus 10. So we're going to hit x, and we're going to square it, and then we're going to do plus 10. And the first window that we're being asked to use is just a standard window, which is negative 10 to 10 for x, negative 10 to 10 for y. And instead of taking the time to type all that in, just go to Zoom, Standard, which is option number 6. So if I graph this, notice I don't see anything. So in this particular window, we see nothing. So obviously this is not the best window choice. So now we're going to change it a little bit. So let's look at option B. I'm going to go to Window, and for my x's, I want my x's to range between negative 10 and 10, which is already what I have in my standard window. But this time we're going to change the y's to be between negative 20 and 20. If you want to adjust that y scale and boost it up to a 5 or a 10, something like that, you certainly could. You don't have to. Let's hit Graph, and now we see a graph that looks sort of like this. Not too bad, but it's a little bit high on my window. So it would be nice if we could maybe lower this a little bit. So let's look at option C here. Let's go back to Window, and this time we're going to change our x's to be negative 5 to 5. So negative 5 for the x-min, positive 5 for x-max. I'll keep the x scale 1. And for my y's, I'm going to start at 0 for my y-min and go up to 35. And I'll leave my y scale at 5. Hit Graph, and now that graph is really become the central focus of my window. You can see it nice and clearly. It's hitting right on that y-axis at a height of 10 there because we were going by a scale of 5. So this is a really nice looking graph, I would say. Okay, let's try the last option and see what happens if we change our x's to negative 1 to 1. So x-min of negative 1, x-max of 1. And I'm going to change my y's to go from 0 to 20 and hit Graph. Now by narrowing that x window from negative 1 to 1, what we're really doing is kind of zooming in a little bit, and we're seeing this really flat looking graph. So that would be a little misleading. It almost looks straight. So it doesn't seem to have that nice parabola shape that we would expect to see with an x squared plus 10. So the best choice here, the best window choice, would probably be option C, negative 5 to 5 and 0 to 35. Okay, now we're going to see some of the other things that we can do with our graphing calculator besides just graphing. So let's go and sketch the graph of y equals x squared plus 4x minus 12. So go to your y equals, clear it out, and we're going to type in x squared plus 4x minus 12. And as always, what I usually like to do before any other window choice is I always start with that standard window, just to be safe. So just to kind of get a rough idea of what am I looking at and how am I going to have to modify this. So let's go to Zoom, Standard, and just see what we are looking at. And make some predictions ahead of time as to what you expect that graph to look like. We have the graph x squared plus 4x minus 12. So this is another parabola again. And because that x squared is positive, we should be expecting to see this U shape pointing up. So we're pretty close to that, except we're missing that bottom part of the U. And that's going in the Y direction, going down. So if we want to modify our window so we get a more complete picture, what we're going to need to change on our window is this Y min, because it's not going low enough for us to see that minimum vertex on our parabola. So let's go to Window, and the one number here that I really need to change is that y min. So let's maybe lower it to -20, just pick something and see if it works, and hit graph, and now that looks a lot better. You can see these tick marks on the y-axis are pretty close together, so if you wanted to change that y scale, you certainly could. Okay? So now what we want to do is, now that we have a fairly good graph to look at, we want to use this graph to find the solutions to where this equation would equal to 0. Now, hopefully you know how to do this algebraically, which means how to solve it without using a graph or a calculator at all. So just to kind of review that a little bit, look at this equation. It's a quadratic equation, so you have lots of options for how to solve quadratic equations. Probably one of the first ways that you would learn is to try and factor to see if this would have a solution that's pretty easy to get. So in this case, does x squared plus 4x minus 12 factor? If it does, we would want to use reverse FOIL here. We would need an x and an x to get x squared. And if we use a 6 and a 2 to get that 12, that has a difference of 4. And since I want a middle term of plus 4, then I'm going to need a positive 6 and a negative 2 so that my middle term will be positive. And double checking, positive 6 times negative 2 is also negative 12. So all my signs are correct. So that means it does factor, which means this factor is going to have as its solution negative 6, and this factor is going to have as its solution positive 2. So my two solutions should be negative 6 and positive 2. So that's called the algebraic way of solving this. Now I want to show you graphically how you could get that same solution. And we'll see why in a little bit as to why that's necessary. If you already know how to solve it algebraically, why do we have to bother graphing it? Well, sometimes equations don't always come out so nice. Sometimes they don't factor. Sometimes they're very difficult to solve by hand. So when that happens, you really need to rely on technology to help you get at a solution. So here's how we're going to do this. If we want to know where this graph, where this equation equals to 0, the first thing you have to realize is finding out where this equation is true means finding out when y is 0. And y equaling 0 represents these two intercepts on the x-axis, because that's what an x-intercept is. It's when y equals to 0. So this parabola hits the x-axis twice, which is why we're going to get two solutions. And so let's figure out how we can find those two intercepts, or those two zeros. And there's lots of names for these things. These are sometimes called zeros, sometimes they're called intercepts, and sometimes they're called roots. So all three of those names all imply the same thing, where the graph hits the x-axis. So there's a nice command on your graphing calculator that enables you to find the zeros, and it's under this calc button right up here across the top above trace. So if you hit second trace, here's a list of things that you're able to do on your graph. And the one that we're going to look at first here is the 0 command. So that's number 2, or you can arrow down to 2 and hit enter. And it's going to ask you some questions so that it can kind of narrow down where that 0 is. So the first thing it wants to know is a left bound. And right now my cursor is flashing at 0, negative 12. You can see those two ordered pairs down at the bottom. If we wanted to find this 0 on the right side, over here first, what I would suggest doing is move your cursor or your arrow to the right. You want to get that little flashing icon as close to the x-intercept as you can, but we want to be slightly to the left of it when it's asking for a left bound. So that looks pretty good to me. It's a little bit to the left, and in this case that also means a little bit below that x-intercept. So what you do once you move your cursor in position is you hit enter. Now you'll see this little arrow on the top up above that marks where that left bound was, and now it's asking for the right bound. So we're going to move our cursor a little bit further to the right, And this time I want to be a little bit to the right of that intercept, which on this graph means a little bit above it. And I'm going to hit enter again. And now you should see those two little arrows, which means the real zero, the real intercept, is somewhere between those two bounds. And this time it's asking, well, what's your guess? Where do you think it is? So arrow back down or to the left a little bit until you get that cursor as close to that actual intercept as you can get. So to me that looks pretty good. Hit enter, and here it is. The 0 is at x equals 2, y equals 0, which is the solution that we got over here algebraically. Okay, let's try that again, but this time let's try it for finding the 0 on the left side. So I'm going to repeat this whole process. I'm going to go to that calc button across the top. So I hit second trace, and I'm going to do the 0 command, so that's number 2. And this time, this time I want a left bound that's close to my x-intercept over here on the left. So I'm going to move, well, I think I hit something. Let me go back and hit calc again. Sorry about that. My pen here is very sensitive. So notice where my cursor is. It's way over here on the right. I need to get it over to this one on the left. So I'm just going to hit that left arrow button until this point moves all across the curve. And right about here is where I think the actual intercept is. So I want to go just to the left of it. So hit that left arrow button a little bit, maybe 2 times or 1 time. And you're slightly to the left of the x value, but on this side of the graph that means you're slightly above it as well. Hit enter. And now we want to go slightly to the right of our intercept. So arrow to the right, there's where that intercept is. I'm going to hit the right arrow button once, so I'm just to the right of it, which on this side of the graph means I'm a little bit below the intercept. Hit enter. And there's my 2 little arrows, so the intercept is somewhere in between. And now for my guess. So I'm going to arrow back to the left, so I'm right over that 0, hit enter, and my 0 is exactly at -6, 0, which was the other solution that we found. So using that 0 command can really help you locate your x-intercepts, or what we call zeros, or what we call roots. And it's especially important when you have very messy equations that would be really difficult to solve by hand. Now, using the same equation, not only can we solve equations using our graph, we can also solve inequalities. So this time I'm going to use the same parabola, x squared plus 4x minus 12, but I want to know where it's less than or equal to 0. So let's draw this on a separate little piece of our notes over here. We already have the graph over here, but I'm going to show you over here. It looks approximately like this. Remember, this was at 2 and this was at -6. So if we're trying to solve the inequality of where this is less than or equal to 0, imagine where 0 actually is. 0 was that x-axis. So that's when x equals 0. So x greater than 0 would be this way. X less than 0 would be this way. Excuse me, not x, but y. We're trying to find where these y values are less than 0. So this is when y equals 0, sorry. And this would be when y is less than 0. So we're trying to find out where the y values of this parabola are less than or equal to 0. So when y equals to 0, that's that x-axis. So where y is less than 0 means we're looking for what part of this graph is below that x-axis for all these negative y's. And the part of the graph that's below the x-axis is just that little part right there. So the solution that we're looking for is this region right here. And typically when you're trying to solve an inequality written this way in terms of x's, the answer that you're trying to give are the x values that correspond to this piece of the graph. So which x's are we using if we're looking at this lower piece of our graph? We're looking at all these x values right in here, which start at -6 and stop at 2. So we're looking for x's that range between -6 and 2. How about the actual endpoints themselves? If x equals -6, is the graph going to be less than or equal to 0? Yes, because that's where it actually equals 0. So we do want to include -6 with an equal bar, with a bracket because of the equal bar, and we also want to include 2 because that's the other 0 that's going to make this equal as well. So our solution for the x's that make this inequality true would be -6 up to 2, including those 2 endpoints. All right, let's try this again, but this time I want to know, where is this graph? Here's 2, here's -6. Where is this graph greater than 0? So remember, when it's equal to 0, when the y is equal to 0, that's the actual x-axis. So greater than 0 would be any part of this parabola that lies above the x-axis, which is all of these points and all of these points. And what x coordinates do those points correspond to? Well, to get all of these points to the left going up, that means we're using these x values going in this direction. And to get these x values, or this part of the graph over here on the right, we want to use all these x values going to the right as well. So let's write these 2 little intervals using interval notation. The one on the left over here goes all the way to the left, which would be -infinity, and it stops at -6. Now, do I want to include the -6? This time, no, because there's no equal bar on my inequality. It was strictly greater than 0, not greater than or equal to 0. So we don't get to include the endpoint. So we're going to put a parentheses around it. And the convention is always to put parentheses around infinity or -infinity. So that's this left piece. Let's write the right interval. This interval starts at 2 and goes all the way to the right. So 2 up to infinity. And again, we don't get to include the 2 because it was strictly greater than, and you always put a parentheses around an infinity. Now, since I want both of these, we put a union symbol in between. So all the x's between -infinity and -6 and 2 to infinity will give me y values that are greater than 0. So you can use a graph to help you find zeros and solve inequalities as well. Okay, let's try another example. This time we want to graph x cubed minus x plus 0.38 in the standard window. So let's go to our y equals, clear this out, and we're going to type in x cubed. Now there's lots of ways to do that, but probably the simplest option is just to hit your X button, and then you use your power key, which is this greater than, or excuse me, this little caret button, and then a 3. So there's your x cubed. Let me just show you one other option. Under math, this math button right here, you'll also see some commonly used expressions, and in option 3 here, that's the cube button. Option 4 is cube root, and option 5 is an xth root. So if I wanted to get an x cubed, I could just type in number 3 here, and that automatically puts that cube on there. So that's another way to get x cubed. Then we want to subtract x, and then we want to add 0.38. And it says to do this in a standard window. So let's go to Window. I've got mixed up dimensions here, so I'm going to just go to Zoom 6 for Zoom Standard, and that will automatically change those window settings to -10 to 10 for x and -10 to 10 for y. So this is the graph that I see. And what we want to do for this question is find out how many x-intercepts are on the graph. So if you look at this graph, It's a nice cubic shape, but it's a little tight. I mean, we have a lot of extra space to the left and to the right that don't really show us any part of the graph. The majority of the graph is right here in the center, and it looks like there's obviously an x-intercept over here on the left side, but it's really hard to see what's happening to the right. It's possible that this cubic just sort of touches the x-axis and bounces right off, or even though we can't see it very well, it may dip below slightly that x-axis and then pop back up again, or it may get really close to the x-axis but not actually hit it and pop up again. So we have to figure out what's really going on over here on that right-hand side. We obviously have a y-intercept on the left because I go up and over that x-axis, but the question is, how many do I have to the right? So we're going to need to modify our window a little bit, and notice what I mentioned before is we have a lot of extra space on the left and the right that don't really show us any key parts of the graph. So that means our x-min of -10 and our x-max of +10 are probably a little bit larger than they really need to be. So one thing I might adjust is to make that x-min and that x-max a little more narrow. So maybe -2 to 2 or -3 to 3, something like that. And that will focus us in just in the middle section, which is where we're trying to explore a little bit more. Another thing to consider is that that y-intercept. Remember what happens over here. If x is 0, what is y? Y is 0.38. That's a pretty small number, and we're trying to find out where this graph hits that x-axis, so we really only want to consider what's happening right in here, a pretty small window. So we're going to narrow our x-min and x-max, but we also probably want to narrow in our y-min and our y-max and not make them nearly so tall, since I'm really just trying to find out what happens right around y equals 0. So let's go to our window, and let's narrow in our x-min and x-max. I think I said -2 to 2 before. We can always come back and adjust this if this doesn't seem like a good choice. And for the y-min and y-max, remember, we're trying to find out where this graph hits y equals 0. So it would be good to decrease this range so that we're close to 0. And -10 to 10 shows us a lot of y values. So let's narrow this down. Initially, I could just try -1 to 1, and let's see what happens. Okay, so here's that x-intercept on the left, and just from this picture, it's kind of looking like the graph is hitting that x-axis and then bouncing right off, but it's still not convincing to me. So I might want to modify my window even further and kind of zoom in right around that x-axis a little bit more, just to be confident about how many times it's hitting on this right-hand side. So let's go back to our window. I'm happy with how the x's are, but I would like to make this y range get narrower, not quite as large. So let's go back to window. I'm going to leave my x's the way they are, and I'm going to change my y-min and y-max to something even smaller. So let's try -0.1. So we're going really small here to 0.1. So I'm going within a tenth above and below 0. So I'm getting really, really tiny. Let's see what this looks like. Now, it's not a very good graph because you're not seeing that nice, complete cubic shape, but notice what happened over here on the right-hand side. You start to see that little dip below the x-axis, which is showing you that this graph doesn't necessarily bounce off the x-axis, but it does go below it a little bit. And again, we're going to modify this window one more time to see if we can show that and exaggerate that little dip even more. So I'm going to make those y-mins and y-maxes even tinier so that we can kind of zoom in on this little window over here. So let's change our y-min. Let's make it an even smaller decimal. Let's try -0.01. Whoops. Get rid of one of these ones. And go from -0.01 to +0.01 and hit graph. And there you can see pretty convincingly that we have 3 intercepts. I have 1 on the left and I have 2 on the right, because the graph does dip below that x-axis and then come back around. And if I hadn't zoomed in on my window enough, I wouldn't have been able to convince you that that really was happening, because from the bigger picture and the bigger window, the graph just looked like it was bouncing right off that x-axis, in which case we would have only had 2 intercepts when there's really 3. So our answer over here is that there are 3 intercepts. And that's because our graph is doing something like this. Bounce down and dip below and back up again. So we have 3 different intercepts. So does this view of our graph, this little narrow view that we have that's showing us that we have 3 intercepts, does that represent a good window for a global view of this graph? No, it doesn't show us that nice cubic shape that we're used to. But if we hadn't zoomed in, we would have missed the fact that there were 3 zeros here. So sometimes you have to use multiple views of a graph. You might need a global view with a bigger window dimension and a closer up view that's necessary to see those smaller details. So you may have to jump back and forth between different windows. Okay, we're going to talk next about how you can use a graphing calculator to find an intersection between 2 different graphs. So this time we're going to graph x cubed minus 4x and 2.31 square root of x plus 3 on our calculator. So let's go to our y equals, clear out our last graph, and in y1 we're going to type in x cubed minus 4x. So I'm just going to do x raised to the third minus 4x, or you could use that cube button under math. And then I'm going to arrow down to y2, and I'm going to type in 2.31. And then I want the square root button, which is right here above the x squared in blue. So we need to do second x squared. Notice I automatically get parentheses in there, so I'm going to type in x plus 3 because I want all of those underneath that radical, and then close my parentheses. Let's graph this in a standard window to begin with. So go to Zoom, Standard, option number 6. There's the cubic, that nice cubic shape, and there's that square root shape that we're looking for. So in this window right here, how many times do these 2 graphs intersect? Well, obviously there's one intersection point over here on the right, but over here on the left, it's a little bit unclear because those graphs are really close together. It's possible that the graph just hits the cubic once and skims right off, or if we zoom in enough, it's possible that it passes through and hits that cubic graph twice, or if we zoom in enough, maybe it just barely skims the top and doesn't hit it at all. So we're going to have to narrow in our window a little bit and see if we can figure out what's exactly happening over here on the left-hand side. So let's see if we can find some of these roots or these intersection points. And I'm going to show you a way to do that on your calculator using this calc command up here on the right above trace. So let's hit second trace. And this time what we're going to do is we're going to use the intersect command, which is option number 5. And so what it's going to do is it's going to ask you for what's the first curve that you want me to intersect. And right now my curve is on this cubic right at the origin. You see that cursor flashing. And let's go ahead and find this intersection point on the right hand side, the one that's a little bit more obvious what's happening. So what I want to do is move my cursor to the right until I get that cursor as close as I can to the intersection point. And you could either be here or here, it doesn't really matter. Once you get it as close as you can get, and it's telling you which curve you're on right up here at the top, hit enter. And now it's asking, okay, well, what's the second curve that you want to intersect it with? And if you move your cursor left, you'll see that now you're moving on that square root curve. And I'm going to move it right as close to that intersection point as I can get. Hit enter. And then it's going to ask you for a guess. And I like where my cursor is right now. I think that's a good guess. So I'm just going to hit enter. And there's my intersection point. Okay, so one of my intersection points, I'm going to round off here a little bit. I'll use 3 decimal places, is 2.485 for the x value, comma, 5.410 for the y value. And that's for the one on the right hand side over here. So that's this one right here. Okay? So we obviously know there's at least one intersection point. Now what we want to do is see if we can find out if there's one over here on the left hand side. Potentially there's 1, 2, or maybe none at all. So what I want to do is see exactly what's happening in that little region. So I'm going to show you a new way to zoom. And there's many, many ways to zoom, and I'm sure many of you know lots of different options and are very capable of using your graphing calculator in other ways than what I'm showing you. But one option that's kind of a nice thing to do is to use what's called a zoom box. So hit zoom, and Z box right at the top is what I'm talking about. And this enables you to create a little tiny box around where you're interested in zooming in. And notice I'm not actually on a curve at all. I'm just floating around in space, and I want to look right in here. So I'm going to make a little box, and this first little cursor that you're setting should be the upper left corner of your box. So let me show you over here for a moment. What I'm really trying to do is zoom in right here. So when you do a zoom box or a Z box, you need to tell it the upper left corner of where you want to be, and then the upper right corner, or the lower right corner of where you want your box to stop. So it's going to ask for this corner and then this corner. So if I go back over here, that position of that cursor looks pretty good for my upper left corner of my box. So I'm going to hit enter, and then I'm going to go down and to the right, and it draws a box as you do this, and you just kind of fit it around the little region that you want to zoom in on. So I'm kind of going to put a little magnifying glass right over that portion of the graph. So that looks pretty good to me. Hit enter again to fix that right corner, and now it's going to immediately modify the dimensions of your window so that you can see just that portion that was in your box. Okay, this looks pretty good, but in this window it's looking like my graph is just skimming that little graph right here, so potentially there's a little intersection point here, but it's still not convincing enough for me. So I'm going to do another zoom box, number 1, and I'm going to move my cursor up into the upper right corner. Let me lower this a little bit. Hit enter, and then I'm going to go down and over to the right and just kind of explore what's happening here a little bit more. Hit enter. Ooh, you can start to see there's a little tiny bit of a gap in between these two graphs. If you're not convinced, you can do it again. You don't even have to hit zoom box anymore. You just move that cursor, and it's just going to keep doing zoom boxes until you quit. I'm going to go down and to the right, just to further convince you that there really is a gap. There's the cubic, and here's the square root, and there is a gap between these two curves. So they're really, really, really close together, but they don't actually hit each other. It's just that they're so close it's hard to see with the naked eye. So in fact, in my graph over here, there is no intersection point on the left side. So there's only one intersection point total. And it was at 2.485 for x and 5.410 for y. Alright, so that's how you can use the intersect command on your graphing calculator to find where the two graphs intersect. Now, let's say I had asked you to do this problem algebraically. So if I took away your calculator, what would it take to find out where these two graphs intersect? Well, if you want to know where two things intersect, you need to see where they equal each other. So if y equals x cubed minus 4x and y equals 2.31 square root of x plus 3, set these two y's equal to each other. So algebraically, what we would have to solve, if you didn't have the technology, would be to take x cubed minus 4x and see where it equals 2.31 square root of x plus 3. And just looking at that, I have no idea how to solve that. It's got a cubic in it, it's got a square root in it. It's going to be a real bear to try and solve this for x because it doesn't fit any of our nice strategies that we might have if we had smaller powers and things like that. So this is really, really difficult to solve by hand. So that's where technology comes in to save the day, because you can pretty quickly graph these two equations, hit that intersect button, and boom, you have your answer very, very quickly. Okay? All right. One other thing I want to show you is how to solve things, intersection points, in slightly different ways. So this time around, instead of writing it as y equals this and y equals that, this time I'm just sort of giving you the already set equal to equation. So I want to find the solutions to this equation. 4x to the fourth minus 3 equals 2x plus 1. And to do that algebraically would be pretty tough to do because it's a fourth degree power. So usually in higher powers like this, the only options that we have for solving them by hand is if they happen to factor out very nicely. And that rarely happens in real life, that something is factorable. So this one is going to be pretty tough to solve by hand if it's at all possible. So that's where you know you need to use technology. Now there's two ways to solve an equation like this graphically. Option number one is, instead of solving this particular equation, I'm going to rewrite it first by setting it equal to 0. So moving all your terms to one side. And you can move them either way. I like having this fourth degree term positive, so I'm going to leave the two terms on the left side where they are, and I'm going to subtract the 2x and the 1 and move these over to the right side. So this becomes 4x to the fourth minus 2x, and minus 3 minus 1 gives me a minus 4. And now you have a 0 on the right hand side. So option 1 is, instead of thinking of this as an intersection between two curves, thinking instead of this as only one curve, and we're going to let our y1 be this left side equation, this 4x to the fourth minus 2x minus 4, and instead of finding the intersection, we're actually trying to find its 0. Okay, so we're going to use our y equals button, clear out what's in here, and I'm going to type in instead 4x raised to the fourth minus 2x minus 4. And let's go to a standard window just to get a clean picture of this. And there's sort of that fourth degree shape. Again, it's a little bit bigger on the x min and x max than I probably need to be, but it's fairly obvious that this hits twice, right here and right here, so it looks like it has two zeros. So let's find the 0 on the left side. Okay, so how I would do that, remember we did this earlier, is to go to calc, which is right above trace. So you're going to go to second trace, and remember this time we were finding a 0 where this equation equals 0. So I want to use the 0 command, number 2, and I want to find the 0 on the left side. So I'm going to go to the 0, it's about there, and to get the left bound, go just to the left of it. So hit that left arrow button once. There's your left bound. There's your guess for your left bound. Hit enter. Now arrow back down to where you think that 0 is, and this time hit the right arrow once. There's your right bound. hit enter. Now go back to where that 0 is, and for your guess, hit enter. So the 0 on the left-hand side, this graph looks something like this. The 0 right here has an x value of negative 0.867, and I'll round that up to a 5. So when x equals negative 0.8675, this equation will be true. Okay, now let's do this again for the 0 on the right side. So we go back and we do second trace, and we're going to find the other 0, so press number 2. And this time I'm going to arrow to the right, and the actual 0 is, whoops, I went too far, is about there. And if I hit the left arrow once, there's a left bound, go back up to that 0 and hit the right arrow once, hit enter, and go back to that guess, hit enter. So this one on this side is at 1.117, 0. So when x is 1.117, we also get a solution. So here are my two x-intercepts. So option number 1 here is to, instead of solving this equation by using an intersect command, now we're setting it equal to 0 first and using the 0 command on your calculator. So that's one way to do these kinds of problems. The other option is to not move any terms around at all, and instead let y1 be this equation on the left side, and let y2 be this equation on the right side. So let's go back to y equals, clear this out, and we're going to type in 4x to the 4th minus 3. There's our left side equation. Then I'm going to arrow down to y2 and type in 2x plus 1. And I'm just going to do a zoom standard. And the one on the left is that, and here's the one on the right. Now remember what we're looking for here. We're not looking for zeros anymore. We're trying to see where the 4th degree equation, that y1, intersects the second equation, that line 2x plus 1. So we're looking for intersection points between these two graphs. And there looks to be one over here on the left side and one over here to the right side. So we'd want to locate those using the intersect command on our calculator. So let's review how to do that. You go to second trace for calculate. And this time we're going to do an intersect, so number 5. And you're going to move that cursor. If I want to find this intersection point on the left side, I'm going to move my cursor. Now I don't see it anywhere. Oh, there it finally popped up. See that cursor, and that looks right where that intersection point happens to be. So I like where it's at for my line. I'm going to hit enter. Alright, now I'm on the second curve, and I'm going to like that point as well. So hit enter, and I like where it's still at, so use that same point as your guess. And there's our first solution. And that doesn't seem quite right because it doesn't match my other 2 points. Let me double check that I typed everything. Oh, see, that's why it didn't match my other solution, because I had a typo. My pen again is pretty particular, so let me fix this real quick. Sorry about that. I had an extra 6 in there that shouldn't have been there. So let's try this again. I'm going to hit graph. My 2 solutions should match no matter what my equation looks like. So there's my 4th degree. There's my line. Let's try this again. So I'm going to do my intersect. So I'm going to do second trace, number 5, and I'm going to go to the left here till I get right over that left intersection point. Hit enter. Hit enter again for my second curve because I like where it's flashing. Hit enter again, and now that's much better because that matches the same x value that we got before. So when x equals negative 0.8675, the y value is negative 0.735 as well. But in this case, usually when you're trying to solve an equation for x, you only need to give the x value. So I'm just going to write down the x value. There's one intersection point. Now let's do it again for the intersection point on the right. So let's go to second trace, option 5 for intersect, and let's go to the right. Get as close as you can. That's too big of a jump, so I'm going to back up a little bit. I like where that cursor is. It's pretty close to the intersection point. Hit enter. There it is again. Hit enter. And I like where it's at for my guess, so hit enter. And that x value is the value we're looking for because we want to solve this equation for x. So if x equals 1.117, we also get an intersection point. So here's your two options again. You can move everything over to one side and get a 0 and use the 0 command, or you can let your left side be y1, let your right side be y2, and then use the intersect command. Personally, I like the 0 method better because sometimes, for me personally, it's difficult to see where those intersection points are. It's not quite as obvious, and it's a lot more obvious to me where zeros occur because you can see where they hit that x-axis. So I prefer to do the 0 process, the 0 method, but it really shouldn't matter. You can do it either way, whichever way is comfortable for you. Okay, we're going to do one last example here. We're going to find another 0, but this time the equation that I'm giving you on the left-hand side here is the equation of a circle. Now, how do I know it's a circle? Well, the reason I know it's a circle is because it has an x squared and a y squared. The coefficients of the x squared and the y squared terms are both 1s, they're both the same, and it's a plus, x squared plus y squared. That's what makes this a circle. Now, if you remember anything about circles, you'll know that circles are not functions because they do not pass that vertical line test. So this is not a function. And that's kind of bad news because on a calculator, remember whenever we're typing in an equation, we have to type it in as y equals. And if something can be written as y equals, that means it can be written as a function. So in order to graph a circle on a graphing calculator, you're going to have to rewrite it by solving it for y first. And I'm going to show you how to do that. So if we have this equation, x squared plus 4x plus y squared minus 5 equals 0, we need to be able to solve it for y so that we have something that we can type into our y equals on our calculator. So here's what we're going to do. I want to solve for y, so I want to get this y squared term by itself. So I'm going to move everything else to the other side. So I'm going to add 5, I'm going to subtract 4x, and I'm going to subtract the x squared. So that's going to give me y squared by itself on the left side. I'm going to put my 5 first, then my minus 4x, then my minus x squared, just to make it look a little bit clean. And that's almost solved for y, except that it's solved for y squared. So what we want to do now is get rid of that square, and to undo a square, we need a square root. So we're going to take a square root of both sides, and technically on the left side, the square root of y squared is not y, it's the absolute value of y. But we can simplify that by saying it is a y, however, it's a plus or a minus of this right-hand side. So in other words, we're not going to get we are going to get two equations instead of one. In y1, we're going to have to let this be the positive square root, which is going to turn out to be the top half of our circle. And then we're going to let in y2 be the negative square root, which is going to give us the bottom half of our circle. And by graphing both of them simultaneously, we'll get the full circle. And you can see that if you individually just did one half of a circle, for example, just the top half, that is a function. And if I just graphed the bottom half, that is a function. It's when we put them together that it no longer becomes a function. So we're going to need to type in these two equations. So here's how we're going to do that. I'm going to go to my y equals, and for the plus case, I can just type in square root. You don't even need to put that plus in front. Just do second square to get that square root button. 5 minus 4x minus x squared, close the parentheses. So there's the top half of my circle. And let's go ahead and draw this top half only in a standard window. So I'm going to do a zoom standard, There it is. There's the top half of my circle. Now let's get the bottom half. So down in Y2, we want to type in the same thing. So you have two options here. You could do negative and use the little negative at the bottom. Don't use the subtraction button. Use the little negative in the bottom, and then you could retype the square root of 5 minus 4x minus x squared. That's one option, and let's go ahead and graph this. There's the bottom half. Okay? Let me show you one other option here. You don't have to do this, but it's something that's kind of nice to know about because occasionally we will make use of this later on in this course. Let me clear out Y2. And what I want you to notice is that Y2, what's in Y2, is actually the same curve that's in Y1, but it's its opposite. So what we could type in Y2 instead of retyping this whole big square root is we could type in minus Y1, or the opposite of Y1. So we're going to hit that little negative button again, and then next I would want to type in Y1, and that's kind of tricky to locate. So there's a lot of steps here. That's what makes this a little bit difficult to do, but once you do it a few times you get used to it. We need to locate and access the Y1 button on the calculator, and it's hidden under here under vars, variables. So if you click on this vars button, this is what you'll see. And we want a y variable because we want y2. So I'm going to arrow over to the right once so that this y vars gets highlighted. And there's lots of different options here, but we're talking about functions right now, so I want option number 1. And there it is right at the top. There's y1, so hit enter, and it's going to paste that in to wherever you just were, where the window that you started in, that's where it's going to paste you into. So let me do that one more time so you can kind of see what I did. I hit my negative first. I'm in this graphing window button. So whatever I access next is going to get pasted back into this window. And to find y1, you hit vars, arrow over once to y vars. It's a function that we're looking for, so just hit enter for number 1, and y1 is right at the top. Hit enter, and now it's pasted that in to y2. So y2 is going to be the opposite of whatever is typed into y1. So if we hit graph, there's the top half, there's the bottom half. So there's our graph. Now if you look at that, does that look like a circle to you? It doesn't to me. It looks kind of more egg-shaped or more elliptical in shape. And that's because of our window. Even though we have our dimensions -10 to 10 for x and -10 to 10 for y, that seems like equal dimensions. It's actually more of a rectangular window on our graphing screen. If you look at the actual physical window on your calculator screen, it's longer in the x direction than it is in the y direction. And you can see that in the fact that the little gaps between tick marks on the x direction are a little wider than they are in the y direction. The y tick marks are closer together. So this is not what we would call a square window. It's actually a rectangular window because the x direction is a little wider, which is what's stretching out this circle a little bit. So there's a way to sort of square up your window and make the dimensions in the x and the y have sort of the same feel. And you can do that by going to zoom and hitting zoom square or z square, option number 5. And now if you look at the little tick marks in the x direction, they have the same distance between them that they do on that y-axis as well, and my graph looks more like a typical circle. Let's look at what the window dimensions actually are. For the window, for x, it's -15.16 to 15.16 for x, and the y is still -10 to 10. So there's kind of a 3 to 2 ratio there for x's to y's. Get 3 times as many x's and twice as many y's. So if you look at that graph again, you have more x's in this direction because it was wider than you have in the y direction. So something to know about, you don't have to use this very often, but sometimes if you want to have a more representative picture, especially when you're talking about circles where it looks more like a circular shape instead of an elliptical shape, then you might try using that zoom square command to help fix your graph and make it look more representative. Okay, that concludes our lecture on using graphing calculators to graph equations. In case you have lost or forgotten some of these commands that we've been talking about today, I just want to remind you that there is a PDF file called Graphing Calculator Commands. It's located on D2L under Content, and it lists all the different commands for what we did today. How to enter in an equation, how to create the viewing window, how to do a zoom box, how to find zeros, how to find intersection points, and it shows these commands for both an 83-84 calculator, which is this first column, versus an 85 or 86 calculator, which is this second column. So if you've forgotten how to do some of these things, print off this PDF file, and hopefully it will step you through all the different commands that we talked about today. All right, that concludes the lecture. Good luck.